Hello and welcome to another section in Algebra 2. This is Unit 6 and this is Section 2, and then we're going to be adding and subtracting radicals. Okay, so the first thing we want to do is identify what like radicals are, and then we want to be able to add and subtract those radical expressions. So when I think about adding and subtracting radicals, I think about the concept of combining like terms. And we know how to combine like terms, right? Well, it's similar to how we add and subtract radicals. Okay. So we've got these, let's say you had this. Let's say you had 3x plus 5x. When I combine like terms, I add the coefficients, and those are the numbers in front of the variable. But when we add and subtract radicals, we do the same thing. So if I have 5 times the square root of 2 plus 5 times the square root of 2, add your coefficients, the numbers that are out front, the integers, and combine those, and then just keep your radical 2, much like you just did here, okay? So let's kind of talk about what a like radical is, okay? A like radicals have the same index and same radicand. All right, well, let's first talk about, a radical, all right? So a radical, I've got this radical symbol here, okay? Like radicals, all right? And so, if I want to say something about the index is the number here. Okay, I'm going to call this n, all right? And that's going to be my index. Okay, and then my radicand is going to go under here. Okay, and we'll just call this r for radicand. All right, and so that's our radicand. All right, so we want to look for, do we have the same index and do we have the same radicand? Okay, so here, all right, what I notice is, I've got these 4 options here. 4 times the square root of 3 times x, 6 times the cube root of 3 times x, okay? Now, these two are not like radicals, okay? Now, if I have the cube root of 3x squared, then, that's different than here, okay? I have the same... in these two, you have the same radicand, okay, of 3x. These have the same index, okay? And then, down here, okay, negative 7 times the cube root of 3x, these two down here have the same radicand and index. Okay, so these that I have here are my like radicals, okay? Okay, they have the same index, okay, which is 3, and then they have the same radicand, that is 3x, okay? And so that's what I'm looking for, okay? Which one have like radicals and which ones aren't, okay? So then, if I were to add these together, if I were to take, like, say, 6 times the cube root of 3x, minus a 7 times the cube root of 3x, then I would just simply take 6 minus 7, okay, which gives us negative 1. So it would give us negative 1 times the cube root of 3x. And you don't need to always put that negative 1 in there. You can just rewrite it as a negative cube root of 3x, okay? And that's how you'd add them together, okay, just like you would if they were just ordinary variables, okay? All right, so then... one of the things that they use is the concept of using the distributive property to add these together, okay? And what you can do is, if you have a problem where it says, 2x plus 3x, what I always do is just take these numbers, add them together, okay, to get me 5, and I just keep my x, okay? But what you're really doing is you can really factor out an x out of here, do the opposite of the distributive property, and then add those two numbers together to give you 5, and you get 5x, okay? So let's go ahead and do that on these 4 examples down here. Now, if I were to add 2 times the square root of 7 plus 3 times the square root of 7, and I'm going to do this a couple of ways. I'm going to do it my way, okay? And that's just take the 2 and the 3, add them together, gives you 5 times the square root of 7, okay? Pretty simple, okay? Their way okay, of doing things means that you take 2 times the square root of 7 plus 3 times the square root of 7. You factor out a square root of 7. Okay, you can either put it on the front or the back end. Let's put it on the back end, actually, because I'm going to do 2 plus 3 and then times the square root of 7. Okay, and that's just going to give me 5 times the square root of 7. So there is a mathematical definition for it, but let's be honest, just take, if you've got the same thing, okay, add your numbers, but keep the radical where it is, all right? And so let's go ahead and take a look at another one. Okay, on this one, you've got 5 times the cube root of 10 minus 4 times the cube root of 10, all right? And all I'm going to do it my way. I'm going to take 5 minus 4, which gives me 1 times the cube root of 10. Okay, and so 1 times the cube root of 10 is just going to be the cube root of 10, and that's my answer. Okay, you could factor out a cube root of 10, take 5 minus 4, it gives you 1. It's whatever you want to do. Okay, on this one, what I notice here, and this is kind of weird because I'm dealing with also some like terms. Okay, notice how each of these numbers in front of my radical contain an x. Okay, so these are all like terms, and then we all have a radical y. Okay, so the square root of y and the square root of y. So one of the things that you could do, this one is kind of tricky. What you'd want to do is just take 6x minus 2x plus 8x, and that's going to 6 minus 2 is going to be 4 plus 8 is going to give me 12. So this is going to give me 12x times the square root of y. Okay, and that's your answer. Okay, if you wanted to take this, let me rewrite it, 6x square root of y minus 2x times the square root of y plus 8x times the square root of y. You can factor out an x and the square root of y. This is one of those where it's a little bit harder to see that you have that as a like term. So then you take 6 minus 2 plus 8. All right, so 6 minus 2 is 4 plus 8 is going to give you 12. Okay, so you just get 12 times x times the square root of y. Okay, and so you've got, we got another one. Okay, now over here, this is an interesting one. Okay, on this one, these are not like radicals. Okay, and I'm going to write that up here, that these are not like radicals. So not like radicals. All right, and so this is it. This is simplified. You can't simplify that any further, okay? You can't factor out a common square root of 5. This is a cube root of 5. These are different numbers. They are not the same. Even though the 5s are the same, your index has to be the same, okay? So this is done, all right? Done. Can't go any further, okay? Can't go any further. Okay, on this one, when you have two different radicals, okay, if you're trying to take this one and perform this operation of the square root of 27 minus the square root of 75, right now they are not like radicals, okay? However, these are radicals that we could simplify. So what I want to do is this, okay? I'm going to simplify the square root of 27 minus the square root of 75. Now, if I take the square root of 27, I can separate that into the square root of 3. Let's do this. The square root of 9 times the square root of 3. Okay, I did 9 and 3 because I can take the square root of 9. Okay, now let's put a subtraction symbol here, and let's split up the square root of 75. I can take out 75. The perfect square that goes into 75 is 25. So I'm going to take the square root of 25 times the square root of 3. Okay, so 9 times 3 gives us 27. 3 times 25 gives us 75. Now, one thing that I'm looking to get this common square root of 3, and here's why. I can take the square root of 9. Okay, so let's go one step further. I get 3 times the square root of 3 minus the square root of 25 is just going to give me 5. So I've got 5 times the square root of 3. All right, so now, with these two numbers, I have a common square root. These are like radicals, okay? So now I just need to take 3 minus 5, and that's going to give me negative 2 times the square root of 3. And that's it. That's my answer. But you have to look for, okay, what would my like radical be? All right, and and if as long as you simplify these down to as much as you can go, then you'll get like radicals, or sometimes you won't get like radicals. We'll look at a couple other examples, but you have to start dividing it into numbers that you can take the square root of. Okay, so use perfect squares when you're simplifying. All right, now here, okay, this one's a little bit different. All right, now I've got the square. Oh dear. All right, this one's a long one. All right, I've got the square root of 8. I've got the square root of 32 times the square root of x. I've got the square root of 200. And I've got the square root of 50x squared. Okay, so let's see what I can do. Let's first simplify our radicals and see if we get any like radicals. All right, so I'm going to do this. I'm going to rewrite this whole thing. I'm going to start doing 5x times, now the square root of 8, I can split that up into the square root of 4 times the square root of 2. Okay, I can take the square root of 4. On the next one, let me do a plus 3. I'm going to do the square root of 32 times the square root of x squared. Okay, I'm going to split those up first if I have a variable. Okay, the next one, plus 3 times the square root of 200. Let's split that up into the square root of 100 times the square root of 2. Ooh, see, look, we're getting 2's out of these. All right, and that's a good thing. All right, then the next one, we're going to do minus 5 times the square root of 50 times the square root of x squared. Okay? All right, so now what I'm going to do, let's take a look at the next step. I can take the square root of 4. So I've got 5 times x times the square root of 4, which is 2, times the square root of 2. Okay? Now on this one, let me split up the square root of 32. So I'm going to do 3 times the square root of 16 times the square root of 2. Okay, now that I've kind of figured out that 2 is my number, I'm just going to take these numbers and divide them by 2. And then times x. The square root of x squared just gives me x. Okay? And then, okay, over here I can take the square root of 100. So I'm going to get 3, so let me do this, plus 3 times 10, square root of 100 is 10, times the square root of 2. Okay? Now, in the next one, let me split up the square root of 50, and let's do minus 5 times the square root of 25 times the square root of 2. And then the square root of x squared is just going to give me x. Okay? All right, so there's a lot going on here, a lot of different moving parts. But, keep your steps in order. Think about, when you guys write this stuff down, are you guys writing this in nice, neat steps? Is everything legible? Sometimes that can help. All right, so the next thing I'm going to do is I'm going to take 5 times 2, which gives me 10x, okay, times the square root of 2, all right, and then plus, 3 times the square root of 16. Square root of 16 is 4, so I'm going to do 3 times 4, and then I'm going to kind of rearrange these, use the commutative property, I'm going to reorder these, and so I'm going to do times x times the square root of 2, okay, and then the next one I'm going to take 3 times 10, so I'm going to do plus 30 times the square root of 2, all right? And then on the next one, I'm going to do minus 5 times the square root of 25, which is going to be 5. So 5 times 5, I'm going to move this x over, switch these around. I'm going to put times x times the square root of 2. Okay, so there's a lot going on. All right, then the next step, all right? We've got this term here, and let me just rewrite that, 10x square root of 2. This term here, 3 times 4 is 12, so I'm going to do a plus 12x times the square root of 2. I have this term, which is just plus 30 times the square root of 2. And then I've got negative 5 times negative 5 gives me minus 25, so minus 25x times the square root of 2. Okay, so now let's think about our like terms. Now they all have a common radicand, okay, but not all of them contain an x. This one does not contain an x. So I'm going to underline all these that contain an x and a square root of 2, and I'm going to combine those. So I've got 10 plus 12, which is 22, minus 25, which is negative 3, times x times the square root of 2. Okay, again, I'm just taking these numbers, adding them, and then keeping the x square root 2. Okay, and then Okay, I'm going to add 30 times the square root of 2, and you can just leave your answer like that. Okay, and that's what I'd prefer you guys to do, because you can't combine those, all right? And that's it. Okay, that's it for that one. That one's kind of tricky, all right? All right, so now let's take a look. We've got this kind of application problem here, distance to the horizon. Okay, so suppose that you and a friend are hiking up a mountain. I would like that friend to be Jim, but he's got other things going on. He's a principal. He's busy. Okay, I digress. Okay, the distance, d in miles, that you can see to the horizon can be modeled by the equation d is equal to the square root of 3h over 2, where h is your eye level height in feet above sea level. If your eye level is 75 feet and your friend's eye level is 50 feet, what expression would you show how much further you can see than your friend? All right, so let's just kind of draw a picture. Okay, this is the height. This is the distance. Okay, and how far can you see? All right, that's that distance that you can see. All right, and so what I want to show is that one friend has an eye level, or our eye level is at 72 feet. Okay, and then our friend's eye level, their height, is equal to 50 feet. And we want to find the difference in the different, how much farther I can see than my friend. So the higher you go, the more you can see. All right, so let's do this. Let's plug this in for h. Let's do the square root of 3 times 72 over 2, and then minus the square root of 3 times 50 over 2. Okay? And so to simplify this, let's go ahead and just see what our numbers do here. Okay, let's take 3 times 72. Okay, if I do 3 times 72, that's going to give me the square root of 216 over 2, and then minus 3 times 50 is going to give me the square root of 150 over 2. Okay, so on the next one, what we want to do, 216, let's simplify the fraction first, and so that's 216 over 2, which is going to give me the square root of 108, okay? And then minus 150 divided by 2 is going to give me 75, so I've got the square root of 75. Okay, now 108, let's figure out a perfect square that goes into that. And that's going to be 36 actually goes into 108. So let's take 108 and let's split it up into the square root of 36 times the square root of 3. Okay, and then minus 75 we've already done. That's going to split up into the square root of 25 times the square root of 3. So we've got a common square root of 3. That's good. Okay, and that's what we're kind of looking for. And if you didn't know how to simplify this one, look at square root of 75. You knew how to simplify that one. That one's pretty easy to see, and then you go, okay, if I can take the square root of 25, I bet that the other, one will have a square root of 3 in it. So that's something that you would try if you couldn't figure that out, and you go, okay, it's going to be square root of 3, take 108 divided by 3, you get 36, okay? All right, so let's move on. You can take the square root of 36. That's going to give you 6 times the square root of 3, and then minus 25, the square root of 25, which is 5, times the square root of 3. And then if you take 6 minus 5, that's just going to give you 1 square root of 3, which is going to give you square root of 3. Okay, so you can see square root of 3 miles further, okay, than the other one. And so pretty cool. And that would be like 1.73 or 1.71, I think, miles further. Okay, so I think that's all I got for this one. I hope you enjoyed it. It's kind of a lot of work. I know it's kind of tricky up in problems like this, but just write everything out. Just think step by step. Go through it, and it'll be all right. All right, see ya. Bye.